Welcome to the second video on stoichiometry and the mole concept. So far, we have looked at introduction to the mole. In this video, we're going to take a look at calculations that are derived or that involve equations. In the next video, we'll look at gas volumes, and in the last video, we'll look at other calculations that have to do with the mole concept and of course stoichiometry. Let's get started. So from the previous information or from the previous knowledge that we have acquired, we are going to start doing calculations that have to do or that involve equations. So we're going to take a look at three types of calculations. The first is where we are dealing with moles. So we'll be given compounds or elements in moles, and we're expected to get something else in moles. The equation is going to be used as a standard of comparison, something that shows us how certain compounds interact. So we're going to start. By the way, we're not going to do any kind of like studying. We're going to learn through examples, because all the information that is in here comes from the previous video. So we're going to learn through examples. So the first example is how many moles of chlorine are required to react with 2.5 moles of calcium to produce calcium chloride. So what you need is a balanced equation for this reaction. So in this case, we haven't been given the equation. We're expected to come up with this equation on our own. So the question is, how many moles of chlorine are required to react with 2.5 moles of calcium to produce calcium chloride? So this is just a simple combination of elements where calcium and chlorine are combined to form the salt calcium chloride, like this. So we know calcium chlorine is a diatomic molecule. It exists always as Cl2, then calcium chloride. So make sure that your equation is balanced. One calcium here, one calcium here, two chloride here, or two chlorines, and two chlorines here. With that being said, let's see how we can tackle this one. How many moles of chlorine are required to react with 2.5 moles of calcium? So how many moles of chlorine are required to react with 2.5 moles of calcium? So this is an equation. This is what always happens. So in this equation, we have 1 mole of calcium reacting with 1 mole of chlorine. So the coefficients or the numbers that are put here, in this case there's no number, so there's an invisible one. So these numbers tells you what are called mole ratios, or how many moles are reacting with how many moles to produce how many moles. So 1 mole of calcium reacts with 1 mole of chlorine to form 1 mole of calcium chloride. So with that insight, now we know the equation, but here we have a situation where we have 2.5 moles of calcium. So the next what they want is to come up with how many moles of calcium chloride are going to be produced. So we're going to write the relationship from the equation. We know that 1 mole of calcium produces 1 mole of calcium reacts with 1 mole of chlorine. So that was just a bit disturbed. Yeah, so let us get back to it. So 1 mole of calcium reacts with 1 mole of chlorine according to this equation. Okay, so now what about 2.5 moles of calcium? So on the side of calcium, we're going to use proportionality. So 2.5 moles of calcium is going to react with how many moles of chlorine? So we're going to do cross multiply, where 1 is going to be multiplied by x and 2.5 is going to be multiplied by 1. So when we do that, we're going to get 1 times x going to give us x, and 2.5 times 1 is going to give us 2.5 moles of chlorine. So even if you think about it, 1 mole of calcium reacting with 1 mole of chlorine mean that whatever mole of calcium we're going to be given, we expect the same amount of moles of chlorine to react with it. Example 2. How many moles of carbon dioxide will be produced by complete combustion of 2 moles of glucose? So this is glucose according to the equation. So this is the equation where glucose reacting with oxygen to produce carbon dioxide and water. So they have said we have 2 moles of glucose. Now they want to know how many moles of carbon dioxide are going to be produced. So this equation is going to help us determine that. So in this equation, we can see 1 mole of glucose producing 6 moles of carbon dioxide, which is good. Then 2 moles of glucose, which have been given, how many moles of carbon dioxide is it going to produce? So do cross multiply. 1 times x going to be x, and 2 times 6 going to give us so this is the cross multiplication, x times 1 and 2 times 6. So some people, they like writing the words, but some, they would prefer not writing this, just to stick to mathematics, and they will keep in mind what they're looking for, which are the moles of carbon dioxide. So what I'm saying is it's okay to leave out the words like more, C6H12O6. Yeah, so even if you solve, it's okay, but just remember what you are looking for. But this is also a very good practice where you can just show the actual things that are involved, like writing the words. Let's go back to our mathematics. So x times 1 is x, and 2 times 6 is 12 moles of carbon dioxide. So the next type of equations we're going to deal with is mole to mass. So in this case, we are going to be given something in moles, and they will need something in mass or in grams. So here's an example. What mass of hydrogen can be produced by reacting 6 moles of aluminium with hydrochloric acid? What mass of hydrogen can be produced by reacting 6 moles of aluminium with hydrochloric acid according to this equation? So I've got aluminium reacting with hydrochloric acid to form aluminium chloride and hydrogen. All right, so they want the mass of hydrogen that's going to be produced when 6 moles of aluminium reacts with hydrochloric acid. So we are concerned with aluminium and hydrogen. So using the mole ratios, we can see that 2 moles of aluminium 2 moles of aluminium produce 6 grams of hydrogen. So this is quite confusing. Where is the 6 coming from? We have 2 moles of aluminium, I understand, but we can only see 3 moles of hydrogen being produced, not 6 grams of hydrogen. So I'll show you the insight. So if we continue with this, assuming this makes sense, 6 moles of aluminium, we expect them to produce x grams of hydrogen. When we do cross multiply, 2 times x is going to give us 2x, 6 times 6 is going to give us 36, and when we divide both sides, it's going to give us 18 grams of hydrogen. So now let me show you the trick. Where did this 6 gram come from? So here's the truth. We know this from our previous video. Number of moles is equal to mass over molar mass. If we solve for mass, we're going to get mass equals number of moles times molar mass. So for hydrogen, since we are concerned with the mass of hydrogen that's going to be produced, we're going to see hydrogen in terms of mass, not in terms of moles. So how do we see hydrogen in terms of mass? So we're going to do some calculation in advance. We're going to say the mass of hydrogen that's been produced, this part which is hidden here, it was 3 moles of hydrogen H2. So we're going to say the number of moles is 3, the molar mass of hydrogen H2, of course, the mass number of hydrogen is 1, so H2, it means it's 2 times 1. So the total mass now, if we apply this formula where N we put 3, and molar mass of hydrogen is 2 times 1, we're going to get the 6 grams. Okay, so this is the insight. So when you have been given something in moles and you want to get something using mass, for example, this aluminium chloride, you can say there are 2 moles of aluminium here, and you get the mass number of this compound. Then you multiply with these 2, what you're going to get is the molar mass. So to avoid doing this, what you can do is just get the molar mass, multiply it by the coefficient here. What you're going to get is the mass of aluminium chloride being produced in this reaction. The next example is how many grams of oxygen are required to react with 0.3 moles of aluminium to produce aluminium oxide according to this equation. So aluminium reacts with oxygen to produce aluminium oxide. So they are saying how many grams of oxygen are required to react with 0.3 moles of aluminium. So go straight to the mole ratios. So the mole ratios here are 4 moles of aluminium reacts with 96 grams of oxygen. Why have we put grams here? Because we want to calculate the mass of oxygen. So oxygen, we have to see it in terms of grams. So 4 moles of aluminium produces 96 grams of oxygen. How so? So if we look at oxygen, there are 3 moles of oxygen. Then the molar mass of oxygen, the mass number is 16, and if there are 2 is 32. 32 times 3 it's 96 grams as the mass. With that being said, we can say now 0.3 moles of aluminium, what's the mass of oxygen that's going to be produced. Then when you do cross multiply here, we're going to have 4x 0.3 times 96. When you divide both sides by 4, we're going to have 7.2 grams of oxygen. Finally, we look at mass to mass calculation. This is where something has been you have been given the mass of something and they want the mass of something else. So here's an example. Calculate the mass of calcium chloride produced when 40 grams of calcium carbonate reacts with hydrochloric acid according to the equation. So calcium chloride reacts with hydrochloric acid to form calcium chloride, water, and carbon dioxide. But they have said the mass of calcium carbonate is 40 grams. They want the mass of calcium chloride being produced. They have given us this mass. Now they want the mass of calcium chloride. Again, we make use of mole ratios. So we say 100 grams of calcium carbonate. As you can see, this is 100 grams. How? 1 mole multiplied by the molar mass of calcium carbonate. So the molar mass of calcium carbonate is 100 grams. So times 1, the molar mass of calcium carbonate is 100 grams per mole. Multiplied by 1 mole, it's going to give you 100 grams. So what about calcium chloride, which is another product of interest? So the molar mass of calcium chloride is 111 multiplied by, if we go to our equation, 1 mole here, it's just going to be 111 grams of calcium chloride. So what do they want? They want the mass of calcium chloride that's going to be produced when 40 grams of calcium carbonate. So if 100 grams gives us 111 grams, what about 40 grams? How many grams of calcium chloride is going to be produced? So when we do cross multiply, we're going to get 100x, 40 times 111. Then we can divide both sides by 100. We're going to get 44.4 grams of calcium chloride. Question 2. Consider reaction below. So we have uranium fluoride here reacting with magnesium to produce magnesium fluoride and uranium. So the question is, how many tons of uranium can be produced in the above reaction using 24 tons of magnesium? So using 24 tons of magnesium, how many tons of uranium can be produced? So again, we make use of mole ratios. So of course there is tons here, which is just another SI unit for mass. It's kg, but 1000 kg makes a ton. So with that being said, according to our equation here, according to our given equation, the magnesium here produces 238 grams of uranium. So what's the mass of magnesium? Of course, it's 48 grams because magnesium is 24. That's the relative atomic mass. So multiplied by 2, it's going to give you 48 grams of magnesium. Then for uranium, it's 1 mole of uranium, and the mass number for uranium is 238. So 1 times 238 is 238 grams of uranium. For those who don't know where the relative molecular mass are coming, or the mass numbers, of course, I'm getting them from the periodic table. With that being said, the question says, how many tons of uranium can be produced in the above reaction using 24 tons of magnesium? So they're asking, what if we have 24 tons of magnesium? How many tons of uranium are going to be produced? Again, cross multiply. 48 times x, we're going to have 48x. 24 times 238. Then we can divide both sides by 48 so that we have x. So when we do the division, we're going to get 119 tons of uranium. So this marks the end of all the equations. So to conclude this video, we're going to take a look at a very short subheading about limiting reagent. So what's a limiting reagent? A limiting reagent is a reactant that is in short supply by the mole ratio and hence finishes before the other reactants are completely reacted. So let's say we are reacting two things, A and B. So as we are reacting, if A is not in or let's say if B is the amount of B present is greater than A. So as the reaction is going, A is going to be depleted. So we're going to have a bit of B remaining. So if that's the case, the A is called the limiting reagent because it finishes fast, and when it finishes, the reaction stops. So a limiting reagent is found by dividing the number of moles of each reactant by its stoichiometric coefficient in balanced chemical equation. To understand what this means, what you do is, if you have an equation that is balanced, to determine which one is a limiting reactant between this and this, what you do is you get the moles of A present and the moles of B present, then you divide by the coefficients. So what I mean is you do this. So you get the ratio of A. The ratio of A is you get the number of moles of A. You get the number of moles of A, you divide by the coefficient, and also for B, you get the number of moles of B, you divide by the coefficient. The smallest number, if this gives you the smallest numbers compared to this, then this is the limiting reagent. If it's this, then this is a limiting reagent. So the limiting reagent is the one that determines how many products are going to be formed, because once it is depleted, then the reaction stops. So in short, the whole point of knowing or learning how to determine the limiting reagent is it is important to identify the limiting reagent before calculating the theoretical yield. What does that mean, theoretical yield? So theoretical yield is just the amount of products that are produced in a reaction by calculations. So when you do calculations, the amount of products that are produced, that is called theoretical yield. It's not the actual yield or the practical yield, it is the theoretical yield, as we are going to learn later. With that being said, we're going to take a look at the last terminology, which is excess reagent. So excess reagent is just the opposite of limiting reagent. Limiting reagent is that one which finishes fast, while excess reagent is a reactant that remains unreacted at the end of the reaction. So once the limiting reagent is depleted, what remains is the excess reagent, and that one will just remain unreacted. Let's take a look at an example to wrap up this. So 19.5 grams of zinc and 9.4 grams of sulfur were heated together. So this is the reaction. Question A, which of the two is the limiting reactant? Question B, how many moles of zinc remain unreacted? Question C, how many grams of zinc element remain unreacted? Question D, calculate the mass of zinc sulfide formed. So all this, like all the how to go about this, we already know, but we just have to consider the limiting reagent. What I'm trying to say is, this last question, calculate the mass of zinc sulfide formed, is the same as the ones we dealt with when we were talking about mass to mass equations, or equations that involve mass to mass. So, but there are these things now which we need to consider, and that is the limiting reactant. So question 1, which of the two is the limiting reactant? So we need to know the number of moles of zinc and the number of moles of zinc sulfide, of sulfide. So of course we use our formula. Number of moles of zinc is mass over molar mass, and when we substitute, the molar mass of zinc is the 5 grams per mole, and that of sulfide is the 2 grams per mole. So when you divide, we are getting 0.3 moles and 0.29 moles. So this number is less than this. So this is the limiting reagent. But remember, we have found the number of moles. This is not the way to determine which one is the limiting reactant. I just did something incomplete. So what we're going to do is we're going to use the ratios for determining the limiting reagent. So the ratio for zinc is this number divided by zinc. How many zinc? What's the mole of zinc? 1. Or what's the coefficient of zinc? 1. So we put 1. Then we go to sulfide. Again, it's more divided by the coefficient here, 1. So when you divide 0.3, 0.29. So this one still is the limiting reagent because it's smaller than this. Question B, how many grams of zinc elements? So this is question A, we have dealt with it. This is question B. How many moles of zinc remain unreacted? How many moles of zinc remain unreacted? So we know that sulfide is the limiting reagent, right? So now they want us to determine how many moles of zinc will remain unreacted. So how many moles of sulfide are going to be reacted at the end of the reaction? 0.29, because that's how we calculated in the previous one. We calculated that the moles of zinc, of sulfide present, of sulfur, so I keep on saying sulfide, of sulfur present in 9.4 grams of sulfur is 0.29, and this is a limiting reagent, so once it is depleted, the reaction stops. Okay, so this is what is going to determine how many moles of zinc are going to be used, how many moles of zinc are going to remain, and how many moles of zinc sulfide are going to be produced. So we know that 1 mole of zinc needs 1 mole of sulfur for this reaction to be possible. So how many moles of zinc are going to react with this 0.29 moles of sulfur? So when you do cross multiply, we're going to discover that, or we're going to get the moles of zinc needed is going to be 0.29 moles of zinc. So we had calculated that the number of moles of zinc present in 19.5 grams of zinc is 0.3. So if 0.29 moles are going to react and the reaction is going to stop, the number of zinc that's going to remain unreacted is 0.3 minus 0.29, which gives us 0.1 mole of zinc remaining. Question C, how many grams of zinc element remain unreacted? How many grams of zinc element remain unreacted? So we have determined that the number of moles that remain unreacted is 0.1. The job is just to convert that 0.1 to mass. So you know mass is equal to number of moles times molar mass. 0.1 times molar mass of zinc is 65 grams per mole. So the mass of zinc that remains unreacted is 6.5 grams. Finally, calculate the mass of zinc sulfide formed. Calculate the mass of zinc sulfide formed. So now we have gone back to mass kind of calculations. So we have sulfide being used because it's a limiting reagent to determine the mass of zinc that's going to be formed. So the mass of sulfur, I keep on saying sulfide, sorry. So what sulfur, not sulfide. This is zinc sulfide, then this is sulfur. So the mass of sulfur present here is 32 grams. Remember, number of moles multiplied by the molar mass. Molar mass is 32, number of moles here it's 1. 1 times 32 is going to be 32 grams of sulfide. And the mass of zinc sulfide, if you do the same, it's going to be 97 grams of zinc sulfide. With that being said, we know that sulfide that's going to be involved in the reaction is 0.29 because that's the one that's present in 9.4 grams. So 0.29 moles of sulfide are going to be used in the reaction. So how many moles are going, what's the mass of zinc sulfide that's going to be produced? And actually, I've used moles. We have to use mass of sulfur here, sorry. So 9.4 grams of sulfur is going to be used. So if 9.4 grams of sulfur is used, what's the mass of zinc sulfide that's going to be produced? So 9.4 grams of sulfur produces X. When we do cross multiply, the 2 grams times X is going to be 2X, 9.4 times 97, and we can divide both sides by 32 grams of sulfur, and we're going to get 28.5 grams of zinc sulfide being produced. This marks the end of this part of stoichiometry and the more concepts. Happy solving.